we're set. Okay. Welcome on in, everybody. Looks like I could... Okay, I think we're good. Let me know if the audio might be a little bit lower. I realized that it was, anyways, but the streaming software had somehow, when it updated, I think had changed some of the audio settings, so it wasn't actually using my good mic anymore. It was using like the computer mic. I was trying to figure out why it didn't sound as good, but I think the levels are a little low, maybe not. Anyways, let me know if there's any kind of issues with the volume or anything like that, and I can try to make adjustments. So where are we today? So a couple things that I want to point out to everyone. So there's a new discussion up that I really would like your feedback on. It's going to help some of us in the future. So there was a Discord. Oh, I'm all blurry. Let's fix that too. Okay, there we go. So, as some of you know, there was a Discord that was put together at the beginning of the semester for this class. That's great. A number of us professors have actually seen an increase in that over the last year and a half or so, to the point where last spring, some of us started talking about, like, we would basically make our own Discord for students to use. So we would set it up so that it's all set for class and that kind of stuff. So you've got like rooms where you can chat with each other for audio, so that you can, it's almost like a study room, but you're in different places. There's different things that Discord is great for. So I guess I would just like this is a graded assignment. So all you got to do is go in there and leave some feedback. If you're a student who hasn't gone to the Discord yet, just join the Discord and then, maybe give your feedback in here. But it would be great to, get what are students actually using in the Discord. I've set up Discords before for other non-school related projects, so I kind of know my way around Discord. But it's always good to get student feedback because, the thing is, you can plan for things, and then the people who use those things have their own ideas about how they want to use it, or So it would be nice to get some feedback, because what I'm planning to do in the fall for my classes is I'm going to have my own Discord, and I'll have it set up so that my different classes can go there and get, they can find the specific parts that pertain to them, and then they can use the Discord how they want to do it. So just kind of give me some feedback. It would be great. I'd appreciate it. And then we can serve our students better in the future with your feedback. So your feedback will be directly helping other students in the future, which, other students current students are now making their other classes better, which are going to help you in the future. So it kind of helps you indirectly, helping other people. So if you could go in there and do that, that's the last discussion assignment that we'll have for this class. It's easy points, easy 10 points. So just go in there. I don't know if the invite to the Discord is still current. Last time I tried to use it, it was, Discord invites die. There's like different ways. You can have a Discord invite where after 100 people use it, it dies, or after 24 hours, it dies. And a lot of times people aren't even aware of those settings, but I think the Discord was maybe not available. So if someone wants to maybe put a fresh invite up there so that anyone who hasn't joined the Discord could at least go there and see what it's about, and then they can make some kind of comment here in there. That would actually be awesome, because I think that's a tool that, like I say, at least 2 of us in the department have had discussions about creating our own Discords. That'd be great. Okay, so that's one thing I'd like you to do. The conic section chapter is open. There's videos in here for you. So there's a video from me, and there's a video from chemistry tutor another video from me, video from chemistry tutor, and then the last one I'll be talking. I thought I had at least one in there, but we're going to talk about parabolas today. There's actually not a terrible amount to talk about. Anyways, we'll go over it in our discussion today. So that's kind of where we're at, and then be aware, it's not that much class left, right? We got a week. So a week from, 8 minutes ago, you'll be taking your final exam. So be prepared for that. I will post a practice test probably Monday. I think probably Monday is when I'll get to it. What is today? Thursday? Probably Monday I'll get it up, and then that will give you some time to work on it. Maybe in Discord, people get together, help each other out with the practice test, stuff like that. And then you'll take your test Thursday. The test is going to be during class, so it's going to be online. I mentioned that before. It was just the way stuff was turned in this time, at least through Canvas, was just too disorganized between me having to sort through pictures from people's phones and then whole PDFs, and then people would submit 8 different PDFs. It was really took me hours, just not even the grading of tests. It took me hours just to organize all the papers and keep track of everybody's stuff. So we're not going to do it that same way. The test will be during our last class session, so make sure you're available then, that you can get that taken care of. If for some reason you have some dire emergency, that work's going to force you to come in or something, talk to me ahead of time and we'll work something out. It's going to be hard to do it late because I leave town when that class ends. So effectively the class is over at that point. And I don't want anyone to get left behind who's, sacrificed their summer and then doesn't pass the class because of a scheduling issue. So make sure that you can make it to that. If you can't, make sure you get a hold of me now and we'll figure something out. Okay. So, basically, common theme that I bring up a lot, don't procrastinate, plan stuff out now so that you're all ready to go. Make sure you're caught up on homework. There's just not going to be any room for extending things past Thursday because the class is over, right? So that's kind of it when that happens. So let's see. You've got some assignments coming due. Notice they're due the 27th, most of them, which is before the exam. So make sure that you're, paying attention to those due dates. I know I have students that get confused about due dates, but they're all in there. They're all available to you. So it's no surprise when things are due. You got a bunch of stuff due in the next week. So make sure you're getting that taken care of, because literally I can't extend these past the 27th because the class ends, right? So make sure you're getting the homework taken care of. We'll continue to talk about stuff. Hopefully you're roughly in the neighborhood of chapter 7, and then it shouldn't be too hard to get to the end. Everyone's in kind of a little bit of a different place, so hopefully that works out for you. Let's see. Let me go back to instructor home. Let me do this. I guess I didn't get the book open ahead of time. I thought I had done that. Text. And we'll move this out separate. We'll do that separately. Close that. So the homework's there, available. What else? I want to make sure I'm not forgetting anything we want to talk about. The retake's going to have to happen Monday or Tuesday just because of the scheduling. So I know most people did pretty well. I don't know if anyone's planning to take the retake, but if you do, that's your opportunity to do it. So make sure you're getting that taken care of, getting your appointment set up, and that you've got your ID, all that kind of stuff ready to go so that you can go take the retake in the testing center. They should have the test and everything all ready to go. And then, so what'll happen then on Tuesday is we're going to cover Chapter 8, Sequences and Series, which actually are not that hard, I think. But some people have a hard time with them just because it's a whole new topic, right? For a lot of people, they're good with math and they're kind of good with going along with stuff. And then when we throw a whole new topic at someone that's just very different than any math they've ever done, they just struggle with it. Some people will just pick it up automatically. So, there's a lot of times there's two camps. There's the people that look at sequences and series and go, yeah, okay, that's pretty straightforward. I get what's going on there. And then there's the people that just are like, what? And part of it is if it's presented well. There's a lot of new notation that can seem weird, and if your instructor doesn't do a good job presenting the notation well, then I know it can be confusing, right? I remember when I learned sequences and series, the instructor actually ran out of time, and they just said, "Read the book." Right? This was back before YouTube existed. Yes, there was a time before YouTube existed. And he just said, "Okay, we'll go read the book." And all that new notation, we were looking at it like, what is this going on? And I remember being very confused and quite frustrated. But now there's quite a bit more resources. And I think it's one of those things where I think I can explain it pretty well, and most people will get the hang of it. So it's not too bad, but you're only going to have a couple days to get used to sequences and series. So, we move fast in the summer. That's just kind of we keep always going back to that. So we'll look at these today, the remaining conic sections, okay? So let's see. Let's get to that if there's no questions. I didn't really get any homework questions or anything, so we'll just dive right into things. And let's see. I want to look this up just so I can kind of show you. Wikipedia, if I recall, has a good image that I like to use. Oh, yeah, this might be the one from Wikipedia. No, borrowed from somewhere else, but that's okay. Actually, let's go back and grab it. I'm just doing this off screen because it's a little dangerous to search for things when you're live because you never quite know what's going to come up. Sometimes something weird might come up. I don't want to be broadcasting it to the class. Here we go. This will work. Okay, conic sections. So you have learned some conic sections, and we are kind of finishing off conic sections as we go. So today, we're finishing them off today. So we've already learned about circles. That was a few chapters back. I don't remember. Today, we're going to learn about ellipses and partially parabolas. You've already learned somewhat about parabolas in your previous algebra, or should have learned about parabolas in your earlier work. So you've got circles, parabolas. The new things we're going to be looking at today are ellipses and hyperbolas. So what is a conic section? Well, the Greeks were basically interested, and they found this kind of thing where they said, well, let's say you take a cone, all right? That's where the conic part comes from, cone. And if you take, like, say you have a wooden cone, like say you just have a wooden cone like this, and you run, a blade through it, bandsaw or something like that, whatever, and you cut off a portion of that cone, what's the shape that you're left with? Like the flat part where you cut? What would that shape be? And that's conic section. So a section, when they mean section, they're talking about like in the medical term, or like if you've probably done this in biology class, where you take a slide of something that's sliced really thin, like so thin that light can get through it, and you're looking at maybe like, if I remember right, a big one was like the onion, where you do a slice of onion and you'd look at onion cells under the microscope in high school. Or sometimes you do it with like a muscle. They slice a muscle so thin that light can get through, but you can actually kind of see the cellular structure inside that muscle or whatever. That's called a section, right? So conic section literally means slicing a cone, right? That's literally what those words mean. You're taking a slice through a cone. And sure enough, from this picture, you can see that's what we're doing. We're slicing a cone, right? So depending on the ways in which you slice a cone, you get a different conic section. So if you, like here, if you make a slice perfectly parallel to, like, say, the base of the cone, then you get a circle. You get a nice perfect circle where you make that slice. But what if you didn't do it at that parallel level? You did it a slightly, not an extreme angle, but a slight angle where the slice goes through, but it still exits the other side, then you get an ellipse. You get a distorted circle, right? And we're going to talk about that connection between circles and ellipses. And I did post those videos. that are up there. So a lot of it's going to be the same. It's even kind of the same examples. But if you're still confused, you can like go back to those videos and watch like take your time and pause and all that kind of stuff to watch what's going on in case you're confused about it. Okay, so I put the video up on ellipses. Let's say you tilt that section even more, that slice, so that it never actually exits the cone. It's just forever. Like the idea behind a conic section is that the cone is infinite, right? It's going on forever, right? So that's, like your parabolas, they don't go up and then stop at a certain point. The idea is we're slicing through them forever. So imagine a forever cone, and you slice through it. It's never really going to exit. You're just going to get that shape. But see that U shape, that familiar U shape, looks like a parabola there? Okay. Now, if you take it even more and you slice at an extreme vertical angle, so perfectly vertical, you get a new thing called a hyperbola. And it's easy to look at this and go, oh, yeah, I get a hyperbola. Isn't a hyperbola just two parabolas? The answer is no. It's actually a very different shape than the parabola. So you want to sort of be aware of that. So basically, you start with, a horizontal slice. You move to a slightly angular slice. So a perfectly horizontal slice gets you a circle. Slightly angular slice gets you an ellipse. More extreme slice angle gets you a parabola. And a perfectly vertical slice gets you a hyperbola. Those are the 4 different types of shapes you can get by slicing a cone. Now, at first, it seems reasonable to go, who cares? I don't slice cones. I don't know anybody who's ever sliced a cone. Why do I care what kind of shapes it makes? And it turns out these shapes are hugely important for lots of reasons. So it's entirely possible that if you're going on to calculus and that whole route, it's possible that in your future someday you will be designing something. If you're going to be an engineer or a scientist or whatever, sometimes you got to design things. And some of these shapes may come in handy because they actually come up quite a bit. These shapes come up a lot in architecture. So when you're building, a lot of times if you take these shapes into account, you can get added strength, which is, of course, important, especially here in Southern California where earthquakes are not, unheard of. You want things to be strong. But there's also lots of reasons, like a flashlight. Why is it that in a flashlight, you can get this nice beam of light where all the light is coming out parallel, and you can just point that beam of light wherever you want, and it shines the thing up? That's because of parabolas, right? You can't really have a flashlight without a parabola. You can have a lantern where the light's just going everywhere, but if you want to focus that onto a certain spot, you need a parabola to do it. There are certain kinds of things you can do with ellipses to get sound bouncing in certain ways. Like if you've ever you ever go to a science museum, like especially when you're a kid, people take their kids to science museums, and a lot of times they have it where you stand there's like a giant room full of people, right? And it's loud and noisy. You stand in one end of the room there's a spot marked on the ground, and then on the other end of the room, your friend is supposed to go stand on this other part, and you can just talk in a normal voice, and in this busy room with lots of people, on the other side of the room, your friend can hear you like you're standing right next to them. And it's weird. It's very strange. And the reason is because that room was designed intentionally with the right conic structure to make sure that all the sound you're putting out bounces off the ceiling and all bounces down to one point right where your friend is, and they can hear you. Okay, so even though you can't hear the people in between you, your friend on the other side of them can hear you when you're just talking in a normal voice. That's because you're using those ellipses. So there actually is quite a bit of design and engineering and architectural importance to these kinds of shapes. Parabolas especially, you probably see a lot of parabolas. You ever see those listening devices where someone's holding like what looks like a little satellite dish in their hand, and they've got the little headphones going to their head, and and then you can be, you could be hundreds of yards away, or well, that might be a lot, but depending on the scenario, you can be really far away, and you can actually hear people talking because that parabola takes all the sound, like your ear is this big, so all the little waves that hit your ear and bounce inside your ear, you get to hear that. But as it gets quieter, it's harder to hear. Well, if you have a parabola this big, and it's bouncing all the waves, the sound waves in this area down to a single point where there's a little sensor that then amplifies that sound up to your ears, then you can hear people at much larger distances. That takes a parabola to do. So, items that you see on a regular basis need these shapes in order to be useful. And you have to understand, if you're going to design a flashlight, you have to know how to deal with parabolas, because otherwise your flashlight's not going to work. It's just going to be terrible, and people aren't going to buy it. Okay, so that's conic sections. That's what we're talking about. So a couple things I want to talk about here. In fact, let's get to the formula. Where's the formula here? Okay, so here's the formulas that we're going to be using today. So we've got the formula for a circle, formula for an ellipse, formula for a hyperbola. So I want you to remember, this is the formula for a circle right here. And remember, HK was the center. So we can, if we have our conic in the right form, we can just look at it and know right where the center is. You just look at it and go, oh, the center is at 1, 3. The center is at -7, 4. You'll know right where it is because the center is given by your H and K values. So just like it was with the circle, that's going to hold for the ellipse and the hyperbola as well. So that's really nice. If you understand how the circle works, then at least the center part for the ellipses and the hyperbolas, it works the same way. You're going to go, oh, there's the center. I see it right in the formula. Okay. The thing is, and I kind of wish we didn't do it this way. I don't love the way we teach circles. I think a lot of students never really recognize the connection between circles and ellipses, but I think it's an important one, because if you're going to, if you're going to work with stuff, you should understand them. If you don't understand them, then you're not going to be a very good engineer or physicist or whatever. We're kind of inconsistent with our formulas. This is very popular, and I suspect it's probably historical. But this right here, this is the most often seen version of the circle formula. So x minus h squared plus y minus k squared equals r squared. And you take the square root of this number over here, that gives you your radius. And then the h and k gives you your center. So it's very easy if you go, let's open another one of these. If I've got, oh wait, we don't even need this. Let's turn it off so I can't, let's see, let's make it y minus 3 Okay, so I didn't even really look at it, but as a reminder, this is how you would graph that. So if you're looking at, let me make this fit the screen a little better, maybe. Okay, so if we're looking at this, my h is 1 and my k is 3, so that means my center should be at 1, 3. Okay. And my radius is the square root of this 9, so that's 3. So really I should be able to go over 3, 1, 2, 3, and put a little point here. Go up 3, put a point here. Over 3, put a point there. Down 3, put a point there. And then when you try to draw your circle, it'll look a bit like a circle. Now, circles are hard to draw, perfect circles. All these conics are hard to draw freehand, so that's why we have these little tools to help us do it. Usually you're going to be using a computer. If you really care about a conic, you're going to be using it in a presentation maybe, or you want a really good version to graphs because it's going to help you with your research. You're probably going to print it out on a computer to get a perfect version. But so the whole idea here isn't to get you really good at graphing conics, because the reality is you don't need to graph conics as part of your job. What you need to do is understand conics. Okay, you need to understand conics so that you can use them and incorporate them in your work when you have to, and be a good engineer or physicist or whatever. So that's really what this exercise is about, is understanding the conics, not necessarily just the emphasis on how to graph them. But that's how we get you to know how they work, is by having you graph them. So if we fill that in, we can see indeed that's how we got our circle. You start here, you go over 3, up 3, over 3, down 3. The center is not actually a point on the circle, and then you have your circle. Okay, we're actually going to do a pretty similar concept with the ellipse, but there's a few differences because the ellipses are a different shape. But the point I was getting at a minute ago was, for the rest of our conics, notice how the rest of our conics, the ellipse and the hyperbola, at least those two, we always have 1 on the right side of the equation in those formulas. Why don't we do that for the circle? And I don't have a good answer. I don't really like the way we do circle formulas, because by putting the circle formula in that same format, you see the connection between the circle, the ellipse, and a little bit the hyperbola, although the hyperbola can be a little bit strange of a conic section. But do you see how our circle formula almost looks identical to our ellipse formula? In fact, it takes a second to figure out the difference and go, I don't know, they look the same. What's the difference? Oh, the difference is that in our circle formula, the denominators are equal to each other, whereas in the ellipse formula, the denominators are not equal to each other. But notice how that's where the part that gives us the radius went. When we divided by r squared, it went down there. So for this form of a circle, if we took the radius, if we took the square root of the denominator, that would give us the radius, right? Well, the same thing's going to happen down here for, it's not the radius, but it's kind of similar, because remember how we did that with the radius, where we just used it to go from the center to the circle? We went in those 4 directions. Well, this acts like that, but in different dimensions. So this one under the x, that, remember, x in graphing represents horizontal, y represents vertical. So you could almost say, like, what I'm about to say is not technically correct, but I'm trying to give you like the concept of what's going on. You can almost think of the square root of a squared as the radius in the horizontal direction, and the y as the radius in the vertical direction. Now, though, I just used those words in a way that is technically incorrect, but you can see what I'm trying to get at. The way the radius up here gives us the distance from the center to our circle, here this gives us the distance from the center horizontally to the ellipse, and this one over here gives us from the center vertically to the ellipse. So it's a very similar idea. We just have 2 different values, because an ellipse is essentially a distorted circle, right? Imagine you've got like a kickball and you squeeze it in and it deforms the other way. That's essentially what an ellipse is. But what you want to recognize is that a circle is an ellipse, right? And a circle is to an ellipse as a square is to a rectangle. So it would be like never realizing that a square is actually a rectangle, and you go, wait a minute, a square is a rectangle? Yeah, that's useful to know, because then any tool that you can use on a rectangle, you can use on a square, right? So any tool that you can use on an ellipse, you can use on a circle, right? In fact, you don't need the circle formula. You're going to have teachers who want you to know the circle formula, but you don't need it, because since a circle is an ellipse, you can just use the ellipse formula for circles and ellipses. You can use the ellipse formula for ellipses. You can use the ellipse formula for circles. Why is that? Because circles are ellipses, right? It's just that when you do it, you'll get these 2 values being the same, but it doesn't make any difference. You'll literally follow the same exact procedure. It's just that the thing you end up with will be a circle. It won't be strictly an ellipse. Okay, I mean, a circle is an ellipse, but you know what I mean. It won't have that deformed shape. It'll just be regular in the way that a circle is regular. So that's what we're going to do. We're going to work to get our formulas in this form, if they're not already in this form. And we're going to do that with completing the square, just like we did with circles, right? It's like literally the identical procedure for circles, except we have a slightly different interpretation, which is why I wish we would just share more of that. Just use the general form for an ellipse, and it solves both your circle problems and your parabola problems, okay? And then we'll get to hyperbolas and parabolas a little bit later here. Okay, let's see where we're at. Let me move this over here so it's out of our way, and we'll get to this ellipse. Okay, so I've got this ellipse, and I've just got it all set up here. I'm slightly cheating because we already have it graphed, but it's because I want to show you how the pieces fit together. Basically what we're going to do, when you do ellipses and hyperbolas, what you're essentially doing is you're building like a scaffolding, like a skeleton of the object, and then you just fill in the shape, right? So in reality, again, this is a sloppy way to do things. But, 30 years ago, well, in the 80s, there wasn't a computer on every desktop and in everybody's pocket. If you wanted a good graph, you were going to graph it by hand, right? But these days, there's such good graphing utilities that that's what people use. But you need to learn how to do the calculations and get comfortable with those things. So that's what we're going to go through. So I'm just going to show you the scaffolding here. So here you can't see the full formula, but here is an ellipse that we're going to deal with right over here. Let's see, it's this one, and let's go ahead. Let's clear this up a little bit for ourselves. Okay, so we have a formula for an ellipse here. And looking at it, I go, man, that does not look like my formula that we just talked about. That certainly doesn't look like, where is it? That certainly doesn't look like this right here, does it? Not nice and clean like that. So that's step number one. We're going to take that equation that we just looked at and we're going to turn it into this form, because once we can easily identify the pieces of information that we need in order to graph that hyperbola. Okay, so step number one, you're going to collect your x's and you're going to collect your y's. It's literally, I'm just repeating the steps that we did for circles, right? The actual graphing part is going to be a little different, but this part where we're doing the algebra, you do completing the square on the x's, you do completing the square on the y's. That's what we're doing. So I've collected my x's together, I've collected my y's together, so that's step number one. And then we're going to start looking at oh, actually, this line was the same thing, wasn't it? I had a duplicate line in there. That's not the one I want. So then what we're going to do is we're going to take the x's and we're going to factor the 9 out. And we're going to take the y's and we're going to factor the 25 out. So basically, for each variable, whatever coefficient is on your square term, you're going to factor that out from that variable. So from the x's, we factored out a 9. From the y's, we factored out a 25. That's all I did in that step. Nothing else fancy going on. And then we're going to start seeing about doing the actual completing the square step. Okay. So now we're going to do that, and we have to be a little bit careful because this is a really easy place for students to make mistakes, because you just have to really pay attention in this step, because if you don't, it's very easy to make a mistake. Like your hand and your brain are not really, like they sort of can be operating separately if you're not paying close attention. So I'll tell you what I'm talking about, because, you know, I grade a lot of tests, and this is kind of commonly where things go wrong. So remember the completing the square step. We're going to take half of 4 and square it. So you take your x coefficient, you take half of it, and you square it. So half of 4 is 2, 2 squared is 4. So I'm going to add 4 in here inside these parentheses. Now, it's really easy because you just wrote plus 4 on your paper, right? I'm assuming if you were doing this problem. We just wrote plus 4 over here. So your brain says, oh, we just added 4 to the left side of the equation. We better add 4 to the right side of the equation to balance that, right? No, not right. The problem here is that, yeah, we wrote plus 4 on the paper, but look, this is inside of parentheses where everything's being multiplied by 9. So it's actually being leveraged by that 9. We wrote plus 4, but we really added 36 to the left side of the equation, because as soon as someone does a distributive property, that 4 becomes a 36. So that's why, to compensate for that, we have to add 36 to the right side of the equation. Okay, so that's why it's 36 over there. And then I come over here, I'm going to take half of 2, which is 1. I'm going to square that to get 1. 25 times 1. So 25. Even though we wrote plus 1, we really were adding 25 to the left side of the equation, which means we need to add 25 to the right side of the equation. Okay? So just watch out for that. That is a very common place that even people that totally know what they're doing will mess that up because they're a little nervous on a test, and it just seems so natural because this is what you always did with lines. Oh, I added 7 to the left side. I better add 7 to the right side. Well, you didn't really add 7 to the left side. You added, some other number. Okay, so once we do that, we need to simplify the right side of the equation, and then we need to do our factoring. The whole point of completing the square was so that we could come up with the perfect squares and factor them, right? That's literally why we do that step, is so that we can then factor things. So when we do that, we get 9 times x minus 2 squared plus 25 times y plus 1 squared equals 225. Okay, that's all I did. Factor the parentheses, simplify the right side of the equation. But when we do that, we are now getting closer. What we're going to do is divide both sides of the equation by 225. Remember, we want, for our ellipse formula, we want a 1 on the right side of the equal sign. So we do a division here. But notice I now have 9 over 225 and 25 over 225. Those can be simplified. So that's the thing we want to do, is we want to do a simplification there. Simplify those things. And now we have what we want. X minus 2 squared over 25 plus y plus 1 squared over 9 equals 1. We are now in that correct form, and you can see that the center is at 2 comma negative 1. Right? And hopefully everyone's comfortable with the signs in here on these values. Remember, in our formula, it's minus, so it's x minus h and y minus k, meaning whatever follows the negative sign is your h, and whatever follows the k, or the negative sign, is your k. And that confuses people because here I have x minus 2 squared. So that means 2 is our h, so I put 2 in here. But what about here where it says y plus 1? Why did you put a negative 1 here and it's a y plus 1 here? Because in order to make it fit the form, we actually need to write it as y minus negative 1. Because it has to fit that form of y minus. But we don't, in algebra, you don't usually write things as y minus negative 1. We just simplify it to y plus 1. But you need to understand how to pull out that value for your center, right, in order to read that properly. So the center's at 2, 1. So let's come back over here. Oops, I don't need that one anymore. Yeah, let's go ahead and leave that page. Let's go over here. Yep, it's at 2, 1, 2, negative 1. Okay, that looks like our center. Okay, but imagine in the real world you wouldn't have this yet. All we'd have is the center, and you'd go, I have no idea where the rest of it is supposed to go. Okay, so here's how this works. So remember how, like, I've been kind of hammering this home because I want you to understand what these formulas are doing, not just memorize them. Remember up here, if we took the square root of the denominator, that gave us our radius. That's the distance all the way around from the center to the circle. Here I said these play a similar role, except this one acts in the horizontal dimension. This one acts in the vertical dimension. So let's look at those denominators and take their square roots. If I do that, let's see, let me go back up to where it was right here. So in the x direction, our horizontal value is 25. So taking the square root of that gives me 5. So just kind of put that in your brain or write it on a piece of paper for a minute. Our horizontal distance is 5. Okay. And what about over here? Our vertical denominator is 9, so we take the square root of that to get 3. So we make another mental note and go, okay, our vertical distortion is 3. So horizontal 5, vertical 3. Okay, and we treat those kind of like the radius, right? It's technically not a radius, but we kind of do it the same where I go, okay, what if I go from this middle point? I'm going to go up 3, and I'm going to go down 3. And then I'm going to go left 5, and I'm going to go right 5. So that's where that 5 and that 3 are coming into play. So the x was horizontal. Square root of 25 was 5, so we went over 5 to the left, over 5 to the right. We got these values. Vertical was 3, so we went up 3, down 3. And then what you would do, and this is why, you know, it's just so much better to print off a computer, but if you were doing this because you were trying to understand something, this is how you would construct it. Now you just try to fill in an ellipse that hits those 4 points. And it's hard to do because, trust me, I've seen thousands of these over the years, and I draw them myself, and I am not an artist. Generally, when people draw an ellipse, it's common for it to end up looking like a diamond, kind of a kite-shaped, where they're not quite getting that roundness in there. Or they can end up looking like an egg or a potato, none of which are good. Right? We want a perfect ellipse, and you give me a potato, and that's, what's the point? So, use a computer when you need it to look nice. But sure enough, that's what we can see. That gave us the scaffolding to fill in our ellipse, and then we would just eliminate all of these other pieces along the way and go, okay, there's my ellipse. Look what a great ellipse I made, everybody. But we had some help along the way using these other tools, okay? And that's how an ellipse gets made. Now you have lots of different versions of ellipses. You can have, ellipses that are distorted horizontally, ellipses that are distorted vertically, all sorts of different scenarios. but they all follow that same formula, that same format that we saw right here. Use completing the square to get it in this form. Once it's in this form, it's pretty easy to work with. Oh, and I didn't actually mention it, but these here are called the major and minor axes. So the major is whichever one's bigger, and the minor is whichever one's smaller. So if we took this, imagine if we took this ellipse and rotated it 90 degrees, it would now be taller than it is wide. So the vertical axis would be the major axis, and the horizontal would be the minor axis. In this case, the vertical is the minor because it's the smaller one, and the major axis is the bigger one. It's the wider one. You know, in this case, it's wide. Okay? But that's kind of what there is to the ellipse. There's a couple more things about that I want to bring up, actually, probably in the book. Let's see. Let me get to the right page. And I'll give you a little bit more in depth in the book here. Let's see. Here's our book. Don't want that anymore. Uh-oh, what happened? Okay, good. It was acting like it wasn't going to let me look at the book there for a minute. And it took me to the parabola for some reason. What did it do that for? I asked for the ellipse. There we go. Okay, so, and here's a version of like what I was talking about with the conic sections. Wikipedia has a nice picture. You can take a look at it. Now, what I'll say is the versions of ellipses we looked at were either horizontally distorted circles or vertically distorted circles. You can get one that's distorted at an angle, like a 45-degree angle, but those are a lot harder to deal with. The algebra to do those gets really, really nasty. And I'm trying to remember where you see those again. If that comes up in Calc 2, might be in Calc 2. Some of you will do that. A little bit in linear algebra probably, depending on the linear algebra class that you take. But those create some difficulties. So the way you get an ellipse is you have these 2 points that are called foci. So most of our conic sections have a thing called a focus. Some of them have 2 focus. The plural of focus is foci, so F-O-C-I. So what happens is you can do this, and you can actually find videos where people have done this on YouTube. So if you want to watch someone do it, and it's easy to do. You basically take a string, you leave it a little bit. You don't want one that's stretchy because that'll distort your shape. But say you take a piece of string and you nail it in here so it's secure. And then you just take all the tension out and you draw around. The shape that you will naturally get is called an ellipse. That's what an ellipse is. And ellipses are hugely important. Ellipses are big if you're going into astronomy. So if you're going to study any kind of, like I was considering studying astronomy when I was younger. Everything in space moves in, not everything in space moves in an ellipse, but for a long time, and even in present day, people who are not sort of familiar with science think that the orbits around the sun are like circular, because that's how we oftentimes draw them. And the truth is they're close to being circular, right? The ellipses are not, the orbital ellipses are not as distorted as the ones that we're seeing, like where we looked here, and it was this, really distorted ellipse. Imagine taking a circle and just distorting it a little bit. That's how a lot of those, especially the closer you are to the sun, that's how those ellipses look, is they're close to being circles. And this was actually a problem because for a very long time, astronomers just couldn't make predictions about where the planets were going to be. And it's weird because now you can literally predict thousands of years in the future. Where is this star going to be? And 10,000 years from now, where's this star going to be? And they'll all be moved a little bit. And we can predict them to a high degree of accuracy. And we can predict where the planets are going to be in, 100,000 years or whatever. But they had really difficult times predicting the planets before. And that's because, we won't go down this whole rabbit hole of science versus non-science. But for a long time, it was believed that those inner orbits had to be circles because circles are perfect. And well, why would a solar system be created with anything that wasn't perfect, right? And as soon as was it Kepler? I don't remember if it was Kepler or there was a few of them right around there that had some interesting stories about them. But I think it was Kepler finally figured out, like, maybe it's not a circle, maybe it's slightly elliptical, and then boom, just like that, all their predictions about like where the planets are going to be made perfect sense. They could start making all these predictions. It's because they were assuming circles when they should have been assuming ellipses. But anything that orbits something else in space does not go in a perfect circle. It's at least a little bit elliptical. So you've got your circle here. As you take those foci and you move them apart, your ellipse is going to get more and more elongated. And as you bring those foci together, they're going to get more and more circular. So what happens is, in fact, like for planets orbiting the sun, the foci are fairly close together, and in fact, the sun is one of the foci. So, what you're orbiting around ends up being one of the foci that you're dealing with. So, at least for the inner planets like the Earth, your orbits don't look like this. For the outer planets, it gets a little bit more stretched out, and you've got the sun at one of those foci. So, just another way in which the ellipse ends up actually playing an important role in things. So here's our formal definition for the ellipse. Let me see if I can. Oh, it didn't make it bigger like it was. That was weird. Whatever I had before was messing it up. Okay, an ellipse is the set of all points P in the plane, the sum of whose distances from two fixed points, F1 and F2, is constant. Right? Because when you're tracing your string is not changing length. Right? That's why it has to be like a piece of string that is not stretchy, because otherwise, when you stretch something, you're literally changing the distance of it, right? But if it's inflexible, you get that same shape. So this side right here plus this side right. Oh, you can't really see it because it's behind me. This side right here plus this side right here, that's constant. That's just the length of the string. So that kind of makes sense when we say the sum of whose distances from two fixed points is constant. Well, okay. These two fixed points are called foci, the plural of focus. The midpoint of the segment connecting the foci is the center. So that makes sense. The center is right in the middle of those foci right there, just like we would expect a center to be. We talked about this. If you cut these lines across through your center, so the longest distance you can have from one side of your ellipse to the other, that's your major axis. The shortest distance is your minor axis. And then you have, your vertex is these two ends. So you can see where they have them labeled here. Your vertex, 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 vertex. The plural of vertex is vertices, which, just so you know. So there's the distance formula, which goes along with the circle. This, just to kind of continue it, this kind of sums it up. You have two foci. You've got a point on the ellipse, and it has two distances to the two foci. Those distances should add up to the same number for everything on there. Right. So I'm trying to find the point where we talk about the foci. So here is here's your general form. This is for things that are at the origin, which I always think it sort of, I don't know, it's kind of weird to do it at the origin and then do it in general. You might as well just learn it in general. But I guess it's a little bit easier here to take in our formulas and kind of see the patterns. We can make sense of this. So here we've got x squared over a squared plus y squared over b squared equals 1. That's the form for our circle. And so notice here what we've got then is a couple of things. We have this relationship that c squared is equal to a squared minus b squared. That's that c value is how you get your foci, right? So you can see for the foci, see how that c value is in there? That's where C comes from. Because it's easy when you're looking in the book, you're like, what's C? Where did C come from? I don't understand what C you're talking about. C comes from your A squared minus your B squared in this case. Okay, so that way you can figure out where the foci is. Why is the foci important? Well, it plays a big role in how you, like in these objects. Like I said, if you're studying orbits, well, the thing you're orbiting around is going to be located at a foci. Okay, in a parabola, if you're designing a flashlight and you want all the, or a satellite dish or radio telescope or whatever, if you have a light source, a little bulb in there, and all the rays are bouncing off, well, that bulb can't just be anywhere in the parabola. It has to be in the right spot so that the photons bouncing off the parabola around it end up all going in the right direction. If you put that foci a little bit, even if it's in the center, but it's a little bit forward or a little bit backward, what you're not going to get a tight beam. You're going to get like an open sort of, cone almost of the light coming out, or you're going to get it so that it's like sort of inverting inside of itself, and then you'll get a cone the other way. So it's really important that if you do this kind of work, that you know where those foci are so that you can design your stuff properly. Okay, so you get all these pieces. You've got your center, of course. You find your vertices, and then you basically fill in the ellipse. And if you need to know the foci, then you come up and you grab your C and you fill those in, and you get it from there. Okay, but it's pretty straightforward. Basically, like the problem we just looked at. So let's look at the general form. Seems more helpful. Where is it? Oh, yeah. So now they're just talking about, basically you take everything we just looked at and you're just going to shift it HK. Remember the transformations that we did earlier in the semester? It wasn't just for no reason. It's because a lot of times those transformations will come up and help you understand the stuff that you're doing. We basically take everything we just learned about the circle at the center, and we just shift everything H, shift everything K. That's the new home for all these things, and they're sitting right there. And you can see how that transformation affected the X and the Y with a minus H and minus K. Remember, that's how we had the same horizontal shift for when we were doing transformations. It's the same thing here. So that's all that's happening. And then they give you kind of a breakdown. There's kind of a cheat sheet here on page 702. So while you're getting used to it, I actually think the way Blitzer does this overcomplicates it. They make a big deal about deciding when A squared is bigger than B squared, and here B squared is bigger than A squared. I think they actually make it more complicated to, I get their approach. They're trying to say, well, when this leads to a vertically stretched circle, or so an ellipse that's tall, and this leads to an ellipse that's wide. But to me, that's overthinking it. Like, you don't need to make it, it's just more stuff to memorize, and we don't, more people memorize stuff the more they don't actually learn it. Just think of it as the way that, we talked about it earlier when we were doing the problem, which is the value that's under the A, that's telling you about the horizontal stretch, and the value that's under the B, that tells you about the vertical stretch. Notice how when we did that problem earlier, I didn't make any discussion about, well, which one's bigger. We didn't need to. We just knew, well, this one corresponds to horizontal. This one corresponds to vertical. I'm a big fan of Blitzer's books, but I think he overcomplicates this one. And then you do it like we just looked at. Okay, and then they've got examples in here. I think that's all I wanted to show you. Oh, right. And then the back page, you can see the stuff I was talking about. Not the back page, but towards the end. So here's the orbits I was talking about. See how when you look at a realistic drawing of them, a lot of times people just throw stuff together and they make it circular. But a realistic one, you can kind of tell, oh yeah, Mercury that's not a circular orbit. And you can see as we get further out, they get less and less circular. Like, it's easier to tell they're an ellipse. That's just how space works, right? And then, like we were talking about earlier, I for many years was taking my kid to science museums, and almost always they have some kind of version of either parabolas or domes. So one would be using, they have like parabola-shaped dishes, and some they have elliptical-shaped domes, where you can do this whole whispering thing, where you stand on the other side of this room and people can hear you like you're right next to them. And in this case, it's an elliptical dome. So, it's actually the stuff being used there. Oh, this is how they do. So kidney stones, where you get this either calcium or mineral formation that forms in your body, and they can be really, really painful, and they can be so big that sometimes your body's just having a hard time working it out. So what they did was that's pretty hard if you think about it. How do you break something that's in somebody's body without breaking the person, right? I mean, you could cut them open, but that's fairly intrusive. Cutting people open is, it's serious because you raise the risk of infection. Someone could have, if someone has some blood issues, some blood clotting issues, that can lead to issues. You don't want them to bleed out. So it's really nice when you can help people without having to cut them open and be invasive right away. And then usually that person, if you cut someone open, they're going to be out of work at least a week, probably, maybe weeks. Just not good for lots of reasons, right? So that's a great question. How do we destroy this stone that's inside of you, or at least break it down into smaller pieces without actually destroying you in the process, right? Well, here's what they do. They have this big elliptical dome, and they stick the stone right at one of the foci. And then what's at the other foci? Well, it's I think it's sound waves they use for this one. So yeah, ultrasound, it looks like. So like sonic sounds, but like so deep you can't really like hear them. Or ultrasound? Yeah, that would be ultrasound, right? So what happens is it doesn't hurt you if you're standing around and it doesn't hurt like your head or anything like that, because your head is not at the foci. So your head is getting some of these sound waves, but there's not like a focus of these sound waves. They're just sort of bouncing all over. But most of the sound waves that bounce off this elliptical shape, they're going to bounce in a way that puts them all at the focus right here. And if they've positioned you well, then what's right at the other focus is your kidney stone. And all those waves build up on top of each other. You get this big amplitude, and then it smashes that kidney stone down smaller. And hopefully being in smaller pieces will be less horrible than when it's in one big piece, right? It's not like it's great, but I've been told it's supposed to be miserable. And then at least then your body can hopefully sort of clear that out, and no one's going to have to cut you open. So lots and lots of reasons why ellipses are really important. Here you have like an actual, what if we had to calculate this? Yeah, what if you did? So that's ellipses. If there's any questions on ellipses, feel free to ask, right? Feel free to ask a question. Otherwise, we're going to move on to hyperbolas. Okay. Now, hyperbolas are a little bit different, but they look similar. This is one where, like, if we look back at our formulas, people kind of think like, a lot of times people think, oh, well, ellipses and hyperbolas are more similar than circles and ellipses, even though a circle is an ellipse. But these formulas really look similar to each other. In fact, what's the only difference in this whole thing? It's the negative sign in between them. That's the only difference in these formulas, which might lead you to believe, oh, well, I bet the shape's going to be really similar then. And it is and it isn't at the same time. It's kind of hard. If you set them up right and you set up the parameters, you can set it up so as you move one parameter, your ellipse gets wider and wider. No, your ellipse gets closer and closer, and eventually it sort of flips inside out, and you get a hyperbola. I didn't set that up, but you can kind of do that. So it's almost like a turned out ellipse a little bit. And it's not really helpful to think of it that way, but they're sort of related in that way. But we take a similar approach. It's different than the ellipse, but we're going to look at these. We're going to identify the center. We're going to look at the A value and the B value down here, and that's going to allow us to construct our scaffolding. Once we've constructed the scaffolding, we're going to build our hyperbola around it. Now, what I will say is the hyperbola is a much more complex shape, and it's actually even harder to make a good parabola than an ellipse. And I already said most people's ellipses either look like, diamonds, eggs, or potatoes. The hyperbola is even worse, right? It's really hard because I would say you even have a little less guidance about how you're building it. So again, if you ever need a real, you're going to show a hyperbola that you graph to your professor, your advisor, just print out a good one, right? It'll just look that much better. You can do your work on scratch work and all that kind of stuff, but if you ever need one that someone else is going to look at, just print a good one off Desmos. So what are we looking at then in terms of the ellipse? Sorry, the hyperbola. Okay, the hyperbola. So they show you there's a hyperbolas get used in architecture. You've seen hyperbolas before, right here, like the lamp. So you've got your lampshade right there. It's up against the wall. The light formation on the wall there, that's a hyperbola. Okay. Now, it's easy to think a hyperbola is just two parabolas. You go, I don't know, it looks like that top half looks like a parabola, so does the bottom half. They're not. The hyperbola actually follows oblique asymptotes, what are sometimes called slant asymptotes. So what that means is they're actually flattening out. A parabola is always a U shape. It's always got a curve to it, whereas the hyperbola is more like a V. It's not a strict V at the vertex. There's a little bit of a curve there, but as you move out, it's getting flatter and flatter and flatter. So as you zoom out on a hyperbola, you actually end up, it looks like two V's rather than, in fact, let me switch over to my hyperbola graph. Let's open this up and turn all this stuff off so that I can show you how to build it. Man, a lot of stuff in this one. Let's turn that off as well. Okay, so our hyperbola. So definition of a hyperbola. A hyperbola is a set of points in a plane, the difference of whose distances from two fixed points called foci is a constant. That definition is one word different than the ellipse. In the ellipse, we said that it was the sum of two distances. Here we are saying it is the difference of two distances. Now, why does that sound familiar? Because that's exactly what our formulas say. It says the hyperbola is a sum, the ellipse is a sum, and the hyperbola is a difference. So you're seeing the words that the words they're giving actually end up in the formula, right? And you can kind of see it here. You've got your foci. These are your vertices, like right where, right here on the innermost points of these curves. Those are your vertices. But we're going from the foci. So at any point on this graph, if you look at these two distances to the foci, the difference of those will add up to the same amount, okay? Oops, I think I wanted that. We've got our general form here. They tell you now about the, notice here for your c squared, it's now a squared plus b squared. So if you were trying to get these values for the foci, now you're going to use a squared plus b squared. But those are easy to grab. Those are just your denominators in the equation. So it's pretty straightforward to grab those. And then remember, then you're going to have to take the square root, but that's going to tell you how far to go from the center to get your foci. Now here's where things do make a little bit of a difference, because when you have a difference, when you're subtracting things, it matters in which order you're subtracting them, right? So notice if you have an x squared minus a y squared term, then what you have is a hyperbola that opens horizontally, right? Like this. If you have a y squared minus x squared, that's when you get a vertical hyperbola where that's opening vertically. So you have to pay attention to, is it an x squared minus a y squared hyperbola, or is it a y squared minus an x squared hyperbola? Once you have that oriented, then basically the way that we construct them is pretty, once you've seen how this is done, it's pretty much the same every time. But it's very easy, I've done it myself more than once, where I go to construct a hyperbola and I accidentally construct it horizontally when I was supposed to construct it vertically. So just make sure you're paying attention at the beginning of the problem so you set that up, and then you don't end up having to go back and redo a bunch of your work, okay? Also, the line going through the middle we call the transverse axis. It's not that Doesn't usually play that big a role, but oh, where am I? Oh, the asymptotes of a hyperbola. So there are asymptotes, which we will look at. I knew there was something I wanted to show you. I'll show you how to construct this box. So this box is all just scaffolding, right? See how we have a box, and then going through the corners of this box, we have these lines. Those lines are the asymptotes. So the book gives you formulas for the asymptotes, but also when we construct the box, it gives you a way to construct the asymptotes, so you can just double check that they make sense. And then once you have all this dashed line stuff in place, that's when you go, okay, I'm going to start at the vertex, and my parabola is kind of going to come over and get closer to my asymptotes. But it's kind of hard to tell like how quickly it gets close to that asymptote. It's really hard to draw those by hand, which again is why you shouldn't really draw them by hand. Okay, but notice that the asymptotes are given by b over ax, and sometimes given by a over bx. But it's pretty easy to tell if you have the right one or not. But notice that's the a and b that come from our denominators. It's the same a and b that we're going to be using to construct the box here. Okay, so once you get those a and b values and you've determined whether this thing should open horizontally or vertically, then you can just go right ahead. You're good to go. Okay. So these, just remember these, we'll revisit these in a second for our hyperbola. And that's, okay, we're ready to jump into the problem now. So let's, where do I have it? Make sure I go to the right thing, right here. And let's do this. Give me 1 second here to prepare it again. I didn't reset the setup after I did the video on them. So I just have to do that. And I got to get to parabolas a little bit too. Okay, so we've got this. This is our hyperbola that we want to graph. So it's the same game that we've done with circles and ellipses. Complete the square. So I'm going to go through that kind of quickly because you've seen it, right? You know how to do it. So we're going to get our x terms together. We're going to get our y terms together. We're going to get those all, grouped. And then we're going to factor out the coefficients on our squared terms from those particular variables. So I'm going to factor a 4 out from my x's. I'm going to factor a 9 out from my y's, right? Just like we've been doing. Nothing new there. We're going to go through and do the completing the square piece. So look at your coefficients on your first degree terms. So your x and your y. Half of 4 is 2. 2 squared is 4. So you can see I added a 4 in there. And then, right, so remember that becomes 16 because it's plus 4 that we wrote in here, but really everything in there is getting multiplied by 4. That's why it's a plus 16 over here on the right. Oops, I'm a little bit off screen. Let me get that out of the way. And then what about negative 81? What do you out of your mind? Where did the negative 81 come from? Well, if we look, I wrote plus 9 in here because half of 6 is 3. 3 squared is 9, so I've got plus 9. But that's being multiplied by a negative 9, right? When we do the hyperbola here, we're actually factoring out a negative 9 because that's what's on the y squared. The coefficient is negative 9, so we factor that out. So notice how that changed the sign on our y term. You got to watch that. I actually did this wrong the first time I set it up. I accidentally missed that, and then I go, wait a minute, this isn't working right, and I had to go back and catch that. So it's easy to miss. But I wrote plus 9 here. It's really minus 81, so on the right side we subtract 81. And then we're going to go through and simplify things a bit. And we're going to get, basically we're going to simplify the right side of the equation. Then we're going to go through and we're going to do the factoring on those parentheses, just like we did for the circle, just like we did for the ellipse. So we get this form. Now you're going to go through and you're going to do the divide both sides by 36 because we want a 1 on the right side of the equation in order for it to fit our formula. So we get this. A little bit more simplifying to do, and we're going to end up with our final a and b values. So you can see it looks like so it just so happens that 2 and 3 both come up twice in this problem because the center, the center is 2, 3, but also those magic numbers we're going to be playing with in the denominators are also 2 and 3 because the square root of 9 is 3, square root of 4 is 2. So just pay attention. The ones on the numerator give us the center. The ones in the bottom actually are the ones that we use to construct that whole box, diagonal box construction, right? And then for the foci, right, we just used that formula we got a minute ago. It's going to be 9 plus, it's c squared is a squared plus b squared. So c squared is 4 plus 9 equal to 13, which means c is the square root of 13, which is about 3.6 approximately, okay? So with all that information, let's just remember, okay, so my horizontal distance we're going to use is 3. My vertical distance is 2. Okay, so when we come back over here to our hyperbola, let's get rid of the actual hyperbola. We've got our center, 2, 3. Okay, we'll come back to the asymptotes in a minute. But first I want to build this structure. So what I'm going to do then, let's see, what did I say? It was vertically 2? Yeah, vertically 2, horizontally 3. So I'm going to go over 3, make a little note. That's a vertex actually. Go over 3, put a vertex. I'm going to go up 2 and down 2. And now we're going to create a box that goes through those 4 points. So it's going to look like this. Okay, see how this is up 2, down 2, over 3, over 3. Now your asymptote should go right through here. Now say you want to know the formula for those asymptotes. We'll just look in the book where I showed you a minute ago. But they're going to be formed from your B and your A. So they come from these, and you go, wait a minute, that's not going through the box. But I'm just showing you. See the 2 and the 3 that we were using? See how they're constructing our asymptotes? And I know you don't believe me yet. Those are the right asymptotes. It's because we haven't translated them. Remember, our center is over 2, up 3. So remember your transformations? Look what we do. I just take these asymptotes, and we translate them over 2, up 3. And then sure enough, they're going to... Oh, look, they work perfect now. So that the one where they were at the origin, that's the intermediate step. You're getting the slope right, and then you move them over to get your intercept right, basically. So now you can see, oh, those are going through the box. Those look like they're going to be our right asymptotes. That's right. So, and then let's see. So our vertices are going to be, did I put the vertices in here? Yeah, right there. So you can see our vertices. So you're going to start drawing from the vertices, and you're going to try to get over near the asymptote. Now, it's hard to know how curvy to make it. Like, getting the round part, it's like just drawing a circle freehand is it's difficult. And then we've got our foci we can put in there as well. And then you just sort of do your best to fill it in, and there's your hyperbola. Okay. Now, all the rest of this junk you can just get rid of, because the only thing that's actually the hyperbola is those red curves. Everything else was just scaffolding to help us get the hyperbola in place. Okay. But that's how that works. So really, you would get rid of all the rest of this stuff. I mean, unless you needed it for some reason. But technically, the hyperbola is just that. Oh, and notice I mentioned, like, see how when we zoom out, it doesn't look like a parabola anymore, right? It doesn't look like a U. It looks like it's really straightening out, and that's because it's approaching those asymptotes. If we put the asymptotes back up here, you can see that those hyperbolas are definitely approaching those asymptotes. Hard to see when we're zoomed in. It's like, I guess they're kind of going to the asymptotes, but as soon as you zoom out, you go, oh, yeah, I get it. Okay, so that's kind of the basic difference right there. Feel free to throw questions in the chat if you got them, or raise your hand, or whatever you need to do. Yeah. Okay. So that's the hyperbola. Okay, good. We'll see how we do with the parabola. There's no question. So you just got to be able to basically graph those things, figure out where vertices are, figure out where foci are, that kind of stuff. You should be good to go. Okay, now the parabola. And you might go, wait, I've already learned about parabolas. I know parabolas. Those are easy. They can be a little bit tricky. Where's the new section? this. Okay, so yes, you have graphed parabolas, but you haven't done it quite like this before. Also, here's these were captured by the Hubble. I don't know how many of you ever pay attention to astronomy, but the new what is it, the Webb telescope that they sent up and is working now. They've done some amazing pictures with that thing, right? Unbelievable. It makes these things that Hubble did look like, you know, a kid drew them with a dull crayon or something. But they took some pictures of this, and if you look, like people make videos of it, you can watch on YouTube or you can find online. They'll put the old Hubble picture next to like the new one that the Webb telescope took. It's unbelievably more detailed. Also, they took that like if you've ever seen it, they redid the what do they call it, the deep field picture, where they took the part of the sky that has the least amount of stuff in it, and they took that picture and you could see there's like thousands of galaxies and stuff. They redid that one with the Webb telescope, and it's unbelievable. They're seeing stuff they didn't even know was there before. It's amazing. Anyways, quick review. This is the stuff you're familiar with when it comes to parabolas. You've done this. Upward parabolas like a bowl, downward parabolas like a hill or a mountain or something, right? This is what you're used to. There's vertex form and there's standard form. Both are useful. Both are convenient. You're going to use both of them in calculus on a regular basis. Those aren't the ones we're super concerned about today. What about, well, we're worried about those, but also now you're going to start dealing with parabolas that are sideways facing parabolas. Now, why haven't you dealt with sideways facing parabolas before? Well, they're a little bit more complicated because they're not functions, right? This is not a function. This clearly fails the vertical line test. This is not a function. This is useful in some cases. Conics can be very useful even though they are not always functions. They're usually not functions. But they can still be helpful. But you always have to keep in mind then, since most of math is now taught from a function perspective, you always have to keep in mind, oh, this thing I'm dealing with is not a function, so I can't make assumptions like that. So the definition of a parabola, this is a little different. Before, when we told you to make graph parabolas, we were basically just giving you a formula to memorize and saying, yeah, here's how you do it. Here's how you graph a parabola. But if you think about it now, you're like, oh, yeah, I was just sort of following an equation, following some directions. I wasn't really like understanding much of what a parabola was. So now we have this idea of a focus that we've been talking about. See the focus now in the vertex? You may not have seen this before. Some of you may have seen it in high school. They used to really teach this when I was in high school. They would really push the whole focus directrix thing. And then they kind of fell out of favor. So it depends where you went to high school. But you've got this focus and this directrix. The directrix is a line. The focus is a point. There's an axis of symmetry. We know parabolas have a symmetry. You could fold them in half. That's all this is saying. If you folded the paper right here, one half of your parabola would lie right on top of the other one. So here's our definition. A parabola is the set of all points in a plane that are equidistant from a fixed line called the directrix and a fixed point called the focus. So right here, your vertex is right in the middle of the line and the focus. Well, what about over here? So let's see. Yeah, here we go. I knew there was another picture in here. Like over here, this point on the parabola is the same distance from the focus as it is from the directrix. Okay, so that's one way of viewing a parabola. And again, this is important because if you're making a flashlight, you got to make sure you get your little LED right where that focus is. If you put it like obviously if you put it off to the side, it's just going to be, you know, it's going to be a mess. It's going to be weird. But even if you get it in the middle, but you put it too far out or too far in, you're going to get light dispersion in a way that is really, you might as well just have a bulb sitting there, right? It's just going to go in all directions. If you want it to come out right, you got to put it right at that focus. Well, if you're going to do that, you got to know how to figure out where the focus is. Otherwise, how are you going to design putting a focus right there? Okay. So they basically say, okay, well, we have this other form of an equation that we can use for parabolas. It doesn't look like the equation for parabolas that you've been using, but it's a little more convenient when you're going to start using when you care about the focus. So there's going to be times when you draw parabolas, you don't care about the focus, right? If you're if you're like, if a lot of times we use parabolas to represent like free fall, like a kicker kicks a football or you shoot a cannonball or something. Those arcs are parabolic, assuming that you ignore wind resistance. It's going to get a little distorted because the thing, longer it's in the air, it's having more wind resistance. But like, you know, assuming we're ignoring all that kind of stuff, you're going to get a parabola so that you can really accurately describe that behavior with a parabola. In that case, you probably don't care about the focus, right? If someone's kicking a football, you know, down a football field in an arc, you're probably not worried about where the focus of that thing is. But if you're designing a flashlight, the whole thing hinges on whether you can figure out where the focus is or not. Because if you can't, then you don't have a flashlight. Okay, so we've got this. Y squared equals 4px or x squared equals 4py. One of those is going to be a vertical parabola. One of them is going to be a horizontal parabola. But I'll show you how to use it because it's actually not too complicated. They're saying that, like in this case, y squared is 4px. Your focus is at this point P, and your directrix is at x equals negative P. So if you can figure out what this P value is, boom, you got your focus and your directrix right there. Same thing over here. If you have this version and you can figure out what P is, boom, you've got your focus and your directrix right out of the gate. So that's why it's important, and that's why it's convenient to use this form of the line, which is not the one that you're necessarily familiar with. Usually what that means is you have to solve for P. So let's look at this example. We've got y squared equals 12x. Okay, so you go, wait, y squared equals 12x. So you come back up to your formulas and go, okay, which one is that like? Y squared equals 4px or this? Oh, it's this one. So the problem we're doing is like this one right here, right? It's what the problem we did was y squared equals 12x. Well, if y squared is 4px and this is y squared equals 12x, then what is p? P is 3, because you would have to break y squared equals 12x would be y squared equals 4 times 3 times x. So you're just breaking that 12 down into the pieces that give you a 4 in front, and then whatever's left is the p value. Okay, so that's what they do here is they go, okay, well, if y squared equals 12x and 4p equals 12, then p has to be 3, right? So that's what they can then say is, hey, look, once we know the p value, we know the focus is at 3, 0, and the directrix is at x equals negative 3. So there it is. The directrix is x equals negative 3. The focus is at 3, 0. Look how there's not a lot of calculations going on here. What a convenient form of the conic. Yeah, it is convenient. So you can do that. So, you know, you have that available to you when you want to do these kind of problems. What was this part? Oh, right. I remember this part. So the here we go. So there's this distance, right, called the latus rectum. So the latus rectum of a parabola is a line segment that passes through its focus, is parallel to the directrix, and has endpoints on the parabola. So basically it's this line segment right here. And you go, why would I care about that line segment? Because it's convenient to tell you how wide that parabola is supposed to be, right? So basically what you do is you get that value, and then it tells you, like in this case, right, so basically we take our equation y squared equals 12x. We plug the values from our point in here. You get y squared equals 36, so y equals plus or minus 6. So it's telling you to go up 6 and down 6. So this gives you an idea of how wide of a parabola you're making, right? Again, you're usually probably going to use a computer for that, but it's helpful to know when you're doing this, when you're trying to analyze the behavior of the thing. And then you can just translate them, right? Imagine we take everything and you just move it over h, up or down k, and then it's the same game, except you just have to translate everything. But they even tell you here, here's where your vertex will be, here's where your focus is, here's where your directrix is. So it's kind of a cheat sheet for you in order to figure out where all those different pieces should go. Because it gets a little confusing. Once you have, it's like when you're programming and all of a sudden you have a ton of parameters and you're trying to keep them all straight. It's a little confusing here in order to do that. And then there's an example where they do one that's shifted, but it's the same idea that we just looked at. And you can see parabolas come up in bridges and different shapes. I thought this was a different shape. I thought this was one you learned it in trigonometry and calculus, where they're like the trig functions, except they're slightly different. I thought that's what a suspension bridge made, but who knows? So this is kind of, this is like what I was talking about, like with a flashlight. It's kind of the opposite. Here they show the Hubble Space Telescope, but like now the Hubble's like old technology. Basically what you have is you've got a light source. It hits the parabola so that all the light is coming out parallel. That's the key to a flashlight. It's kind of amazing when you think about it. All the light is coming out of that parabola parallel to each other. All those photons are going parallel. And it's tricky to get them to do that, because if you just have a light source, the light's going everywhere, right? But if you have the right shape right here of a reflective surface, it turns it all into parallel lines. That's why they can have those beams. You ever see that where they have they'll have it in a big city or something where they just have this beam of light going up into space because they're trying to like advertise their car lot or something like that. You just have a big light with all the light coming out parallel like that. So kind of like a giant flashlight, right? And a telescope is the same thing, but in reverse, right? If you think about what a telescope does, is it creates a lot of light from a big area and it collects it all down so that light goes in your eye or onto a computer screen or into a computer or something. But anyway, either your eye is the sensor or there's some electronic sensor collecting all that light. But that's how they do it. So there's a big telescope collecting a large area of light, and the light coming in all bounces off this parabola in a way that it all collects at the focus, and right at the focus is either a mirror that bounces into your eyepiece, or it is some electronic device that is a light sensor, and it picks up those and then feeds it into a computer or something like that. But it's the same idea, just in reverse, right? You still need to know where that focus is if you're going to build telescopes, just like you do for parabolas. I thought there was another picture. Am I thinking of a different book? Maybe. I must be thinking of a picture in a different book. So anyways, that's what you do with the parabolas. They're not... The parabolas are, as long as you can keep track of all these new letters, like the math is not nearly as hard. Notice that in the parabola section, we were not completing the square. All those big problems where we had to complete the square and stuff, which hopefully you're comfortable with by now, but we didn't even have to do any of that, right? That wasn't necessary at all. Okay. So that's through conics that we needed to cover. So next time we will cover sequences and series. Bring me any kind of questions that you want, although I'll probably have to spend most of the class on sequences and series, I suspect. But then I can hang out after class and help you with any problems that you need, or, we'll figure it out. I don't want to make it like you can't get help, because you can get help. But so Monday, probably Monday, possibly sooner, but count on Monday, I'll post that practice test for you, so you can start working on all of that. Please remember that there is one last discussion for you to do here. It's the one so that I can make a nice, just give me some ideas so that when I'm creating the Discord for my classes in the fall, I'll do it in a way that sort of best works for students, right? So that they go in there and go, oh, we really like if there's lots of audio rooms so we can talk to each other and work on homework together, or, whatever it is that you want. So, please put your suggestions and your helpful tips in there. If someone could post a link to that Discord so that anyone who hasn't gotten into the Discord can do it. Maybe even if someone could post it in here That would be great, because then the people who have like not felt the need to go there can still complete the assignment and get their 10 points. So make sure you get that done. Make sure you're getting the homework done. Make sure you're getting ready for the test. It'd be nice to pass everybody. I'm sure you all want to pass. I would like you all to pass. So let's make sure we're taking that stuff. And then just remember, literally the class ends at the end of the end of the class a week from today. So make sure that you can be done by then, because there won't be any time to do anything else. And if there is going to be a conflict with you taking the test that day, talk to me ahead of time. I'm not going to be able to do much afterwards. Try to get it set up ahead of time if there's some kind of conflict. Okay, good work, everybody. As always, I'll stick around in Zoom and help anybody. As long as you have questions for me, I'll stick around and help you. Otherwise, I'm going to close down the YouTube stream. And have a good weekend, everybody. I'll see you later.